This is research conducted at the Australian National University with Adam Bigot and Kane Townsend. Okay, so there's going to be some overlap with Kane's talk, and I apologize for that. So I'm just going to briefly go over yeah, so this is going to be the outline of my talk. So I'm going to introduce geodetic groups and I'm going to talk about the history. So this is the overlap with Kane's talk. And then I'm going to introduce length functions and talk about how they're related to vast survey theory. And then I'm going to describe some applications of length functions to the classification of geodetic groups. So the definition of a geodetic graph is just when you have when your connected graph has a unique geodesic between any two pair of vertices, and your geodetic a group is called geodetic if you have a Cayley graph which is geodetic, which means you can find a symmetric generating set with respect to which the Cayley graph turns out to be geodetic. So it's important to note that the property of being geodetic, having a given Cayley graph being geodetic, is very much dependent on the generating set. So like the property of, so geodesics don't really map to geodesics under quasi-asymmetry. So if you want to prove that a given group is not geodetic, you need to go over all the Cayley graphs and see that none of them are geodetic. So let's look at some examples. So given any finite group G, you can just take the symmetric generating set to be the whole group other than the identity, like we were saying. So this would give us the complete graph of order G. So this is geodetic, and you can also have odd length cycles, basically just take the cyclic generators of cyclic groups of odd order. So similarly, you have these plane groups as Kim was talking about. So if you take the generating set to be the whole of the finite group, all the finite groups, all the elements of the finite groups other than the identity, the generating set and its inverses, the normal form theory for free products tells us that this is also geodetic. And similarly, if you have two groups which have symmetric generating sets which give you geodetic graphs, just the free product will again be geodetic since S1, since the disjoint union of symmetric generating sets will give you a geodetic Cayley graph. Okay, so these are some examples of geodetic Cayley graphs of C5 star C2. Okay, so going over the history again, so Over proposed the program to classify all geodetic graphs, and Madeline Lorotto conjectured that groups which have presentations which can be associated to these rules, which basically when you apply the rule, the length of the word decreases, and you have these unique normal form. Essentially, the conjecture is that. So the groups which have presentations like this are precisely the plane groups. And Shapiro conjectured that geodetic groups are precisely the plane groups. So to summarize Keynes, the result Keynes was talking about in his talk. So geodetic groups are a proper subclass of the virtually free groups. And the group is geodetic if and only if it has a presentation that's given by finite inverse closed confident let's reduce a gradient system. So this theorem really unifies Shapiro's and Madeline-Rotto's conjectures. Now it's essentially proving that the plane groups geodetic would proving that geodetic groups are plane would essentially solve both the conjectures, and proving Shapiro's conjecture now amounts to just ruling out the case when your group has a non-trivial amalgamation or a H&N extension. So this brings us to length function. So what is a length function? It's essentially a function from a group to the integers such that these three properties hold. So the length of the identity has to be 0, the length of an element has to be the same as the length of its inverse. Then there is this function d defined. So it's essentially d here does not really stand for distance. It's essentially how similar these two elements x and y are. So, but I might still say distance, just so the distance between x and y is just the length of x plus the length. This is the difference. It's just how much the length of x y inverse shrinks as compared to just adding the lengths of x and y. So it can be thought of as a notion of similarity, how much x and y are similar. Because if x is equal to y, you can see that x y inverse is actually going to be the trivial word. trivial element, and it's going to be identity, and so the length of the identity is 0. So whenever x and y are very similar, uh, the d of xy will be large. So some examples of length function. So if you have a free group, you just take the free generating set and just define the length to be the length of the reduced words. So here it's easy to see that it is a length function. So the length of the identity is 0. The length of an element is the same as length of its inverse. And now d of xy here is just the number of cancellations that occur in xy inverse. So essentially this is the largest suffix that they share. So if, yeah, the largest terminal subword of x and y essentially. So those are all the cancellations that occur in x, y inverse. Sending this example, so we have, even if we take a free product of groups and we define the length to be the length of the reduced words, it's easy to see that they satisfy the first two properties. And now the third property, it's a bit trickier. So it really depends. So if L is the length of the largest suffix that they share, now there are two cases for the values of d of xy. So if the L plus 1th letter is distinct, so assume it's distinct, but if they belong to the same group GI, then it turns out that d of x comma y is L plus 0.5. But if they belong to if they belong to different GIs, the length is, the distance is L plus 0.5. But if they belong to the, oh, that is an error. Yeah, sorry. If they belong to the same group, the distance is L plus 0.5. But if they belong to different groups, the distance is actually L. So, and to prove the third property is just a case-by-case analysis, which I will skip. So, and so this example gives us a whole class of examples. Essentially, when you have a group action on a tree, you just define the length function, fix a vertex p0, and you define the length of an element g to be the distance of one and the vertex g p0. So, and really here, the first two properties hold, and here d of xy is just the length of the common path you get when you go from p0 to x inverse p0 and p0 to y inverse p0. It's just the length of the common path that they shared. So how do we see this? So suppose that v0 is p0 here, and wm is y inverse p0, and vn is x inverse p0. So what is the distance? So the d of x comma y is just the length of x. So distance of p0 to x inverse p0 plus the distance of p0 to y inverse p0 subtracted with the distance of xy inverse p0, right? But then p0 to xy inverse. But then the distance of p0 to xy inverse p0 is the same as the distance of x inverse p0 to y inverse p0. So it turns out that d is just going to be m plus n minus of m minus k plus n minus k. So essentially, this is going to turn out to be just exactly k. So k is the length of it's just the uh, index of the word, it's just the length of the common path that they share. Okay, so, and now we're going to see that all length functions actually arise from these group actions on trees. So group actions on trees give us length functions. Now we're going to see that all length functions in fact arise this way. So, and so it's easy to see that the first example, when we had the free group and we just defined the length to be the length of the reduced word, is actually arising this way. It's just the group action of the free group on its Cayley graph, which is a tree. Just take the vertex to be identity, or really any vertex will do. So now we are going to require length functions to satisfy an additional property. So Lyndon calls it the property C0. So he insists that d of xy is always an integer. But this is really a superficial property because we can just rescale the length function by 2 to make sure that it's d of xy is always an integer. So this is Chiswell's theorem that we're going to use. So if you have a length function which satisfies C0, then it arises from a group action on a tree. So essentially what he's saying is there is a tree T and a vertex P0 such that the length of G is just the distance of P0 to GP0. And then Lyndon additionally requires, when he introduced length functions, so Lyndon's the person who introduced the concept of length functions, he required length functions to satisfy this additional property A5, which basically says that if d of xy plus d of xn, if you have two elements of the same length, and d of xy plus d of x inverse y inverse is strictly greater than the length of this element, then x is equal to y. So in the case of the free group, what this means is if the length of the common fix that they share plus the length of the common prefix that they share is strictly bigger than the length of the element, then the two elements have to be the same. So yeah, then this is another one of Chiswell's theorem, which basically links length functions to past series theory. It says that a given length function satisfies A5 if and only if the length function arises from a group action on a tree. And now he's saying that this action stabilizes of each edge is trivial if and only if the length function satisfies A5. So this tells us that the existence of a length function which satisfies A5 will guarantee that the group is plane. So now to work on the geodetic group problem, we now need to define length functions on geodetic groups and or even on non-geodetic groups. So the most obvious candidate for the given length functions is simply just look at the Cayley graph and just define the length of the element to be the distance of one with the element G. So this is a function even for non-geodetic Cayley graphs, but then it turns out that this is not a length function for geodetic graphs. It's a length function for many classes of geodetic graphs, but now we're going to see that it's not a length function for in general. It need not be a length function. So this is the set we are working in. So we have a group and we have a fixed Cayley graph, and we just define this function to be the distance of the vertex 1 with the vertex G. So here d of xy tells you how much small. So we have a geodesic from 1 to x, geodesic from 1 to y. So d of xy is essentially sorry about that. D of xy is essentially how much smaller the geodesic from x to y is when you as compared to just going from x to 1 and 1 to y. So again, here we might need to take 2 times the length function instead of the length function in order to make sure that C0 holds. But then this has no effect on whether the function satisfies property A5 because you are scaling the whole equation by 2. So yeah, so in the case of so this function turns out to be a length function in the case of the free group case because here it's the function that we just defined is exactly the length of the reduced word, and even in the case of the even in the case of free product of groups, it turns out that it is a length function, but we just have to multiply the function by 2 to ensure that d of xy is an integer. And now we're going to look at an example. So you have a geodetic Cayley graph, but then this is not a length function. So the way I'm going to prove that it's not a length function is just assume it is, then it doesn't satisfy property A5. So, but this group is plane. So this cannot be a length function. So we just look at C5 star C2 with the cyclic generators. Now this is, so look at these two elements, b a square b and b a power minus 2b. So these are distinct, they are not equal, but they have the same length. And moreover, if you calculate d of x comma y, it turns out to be 5. And d of x inverse y inverse also turns out to be 5. So their sum is 10, which is strictly greater than 8, which is the length of x, which is equal to the length of y. So A5 does not hold. And And so this is not a length function. And now we're going to look at a function. So now we're going to look at a non-geodetic Cayley graph for which this function is a length function. So this is going to be a very motivating example. So again, the function is exactly the same. It's just 2 times the distance of 1 to g in the Cayley graph. So it's easy to see properties 1 and 2 hold to ensure the similarity property when we need to check this equation. So suppose that you have 2 different elements and they diverge after k steps. So what I mean is the product of the k elements from the right is equal to the product of k elements from the right of like both of these elements. And so these geodesics diverge and they don't meet again. So this is not a geodetic Cayley graph. So it is possible that 2 geodesics may diverge and meet again. So, but I'm ensuring that that does not happen using these 2 conditions. So I'm just looking at 2 different geodesics. I'm just looking at 2 different geodesics. And essentially, to, to so I'm going to assume this. So d of x comma z, z is strictly greater than d of x comma y. So this would ensure that there are only 3 configurations possible. So one is y lies on the geodesics to x and z. So here d of y comma z is exactly the same as d of x comma y, and it's just the distance of it's just k. Basically, they share k many letters in this case. They essentially uh, it does not diverge really. So the y is a part of the geodesic to x and to y. So it's just the whole of y. And the second case is when they do diverge, but in this configuration, they diverge along non-adjacent vertices of the C4 graph. So in this case, again, the length function just turns out to be, so the d of x, d of yz turns out to be equal to d of xy, which is equal to k because, so what is d of xy? It's just telling you how much the geodesic from y to x is smaller when you just, when you compare it to just going from y to 1 and 1 to x. So in this case, uh, so when we look at a geodesic from y to x, so we go along y, and so there are 2 different ways, but then essentially this cancels out. Like, so you just end up with the uh, you just end up with k, like essentially the how much they the common path that they shared before diverging. And then the third configuration is they do diverge in this way, like they diverge along adjacent vertices of C4. So in this case, d of xy is equal to d of yz, but it's equal to k plus 2. So k is how much the common path that they shared before diverging. And in this case, when you look at the geodesic from y to x, so if the geodesic went along this way, it would turn out that it is exactly k, but now we have a shortcut. So the geodesic from y to x is shorter than just going from y to 1 and 1 to, like it's much shorter because there's a shortcut like this. So this essentially causes the term to the d of x comma y to be larger in this case. So this proves that in even when you have in some cases that even when you have a non-geodetic Cayley graph, the function that we defined can turn out to be a length function. So this motivates the next theorem. So the setting is you have a plane group G with a non-geodetic Cayley graph, and you have 2 distinct geodesics started with S1 up to S length of G, R1 up to R length of G. And you assume that the first letters are not equal. Then the conjugate of S1 R1 inverse must satisfy this inequality. So it's easy to see that the this length, the length of the distance of 1 with the conjugate must be less than or equal to 2 to mod G minus 2 because so what is happening here? Yeah, so we have, so what is oh, this is supposed to be an S2 here, my bad. So yeah, so what is S1 inverse G? It's just S2 up to S mod G, and R1 inverse G is just R2 up to R mod G. So these are geodesic. So the length of these two elements, so the distance of these two elements from the identity in the Cayley graph is just 2 times, it's just mod G minus 1. But now the length function is twice the actual length in the Cayley graph. So it turns out that so even if you just do the free reduction, you'll get this inequality. So this must hold. And now you define these two elements, S1 inverse G and R1 inverse G. So these are not equal. So these elements are not equal, but they have the same length. They have length 2 mod G minus 2. So d of x comma y here. So yeah, so if we calculate d of x comma y, it's going to turn out to be this, and we can bound this. So S1 inverse R1. So either the mod of S1 inverse R1 can either be 2 or 1. So in the worst case, it is 2. So we have this inequality, and d of x inverse y inverse just turns out to be this thing here. And then so now we know that since the group is plane, a phi must hold. So, because we know that it is a length function. Since a phi must hold, this inequality, so d of x comma y plus d of x inverse y inverse cannot be strictly greater than the length of x. So it turns out that the conjugate, so this inequality must hold. So then we just get our inequality as given in the theorem. Yeah, that is it. Thank you. Do we have any questions?
Thank you, Josh. Does anyone have any questions?
Yeah, I have one question. Can you hear me?
Yeah, we can hear you.
Yeah.
That's one question. With the C5 star C2, if you take the full generating set for the C5, does that length function always work?
Yes. So that length function, that is a length function. Yeah. C5
Okay.
star C2 with the full generating.
All right. So it's just when
But
you
you just have to take two times the distance of one with the element of the group instead of just
Okay. So the problem is having a non-complete Cayley graph for the finite.
That's right. Yeah. And even if so essentially when they have these properties like so here there are 3 degenerate cases, right? Like 3 non-degenerate cases. So essentially what happens is when they exit through adjacent vertices, there is like an additional level of similarity. So when you have cyclic groups of large order, the similarity is much higher. Like when you exit through adjacent vertices, diverge through adjacent vertices. So that essentially causes the third property to not hold. Like you will have cases wherein the third property doesn't hold.
Okay.
Hi, Joshua. Thanks for the talk.
Hi, Adam. How are you doing? Oh,
Good.
thank you.
Okay, so if no one has any more questions, let's thank Joshua again.